Hey everybody. So today I want to talk to you about resonance curves. And resonance curves have to do with the damped driven harmonic oscillator. So just to recap what we already talked about in a previous lecture, let's assume that we have a damped driven harmonic oscillator, and we're going to assume that this oscillator is moving in a horizontal direction, so we don't have to worry about gravity. And it's being driven by a sinusoidal force. The form that we chose was F naught cosine omega dt, where F naught is the amplitude of the drive force in newtons, and omega d is the drive angular frequency. Now, in addition to this driving force, we also have viscous friction acting on the system. And of course, the equation for viscous friction is minus CV, where C is the damping coefficient and V is the velocity. So, of course, the drag always acts opposite to the direction of motion. Now, of course, it's a spring, so we also have Hooke's law, F is equal to minus kx. So if you do the sum of the forces on our mass, object M, the sum of the forces MA is equal to minus kx minus CV plus F naught cosine omega dt. Now, this is the second order differential equation, and we guessed the solution that the position with respect to time x of t was equal to a times cosine omega dt plus phi, where phi was the phase constant. Now, in a previous lecture, I went ahead and showed you that this guess works in this differential equation, and we solved for our phase constant, and we also solved for the amplitude of the damped driven harmonic oscillator. Now I'm going to focus in on this equation for today, okay? So let's talk about this. The amplitude of the damped driven harmonic oscillator, which I called A, is equal to F naught over M divided by the square root of omega naught squared minus omega drive squared squared plus gamma squared times omega drive squared. Okay, so here yet again F naught's the driving force, the amplitude of the driving force, N is the mass attached to the oscillator. Damping is our damping coefficient, which is our C over M, okay? And omega naught is the natural frequency, which is the square root of K over M. And then omega d is the drive angular frequency. Okay, so this is our equation. Now, we derived this in a previous lecture, so if you haven't watched that yet, be sure and go back and watch that one. But here today, I'm just going to talk about the fallout from this. So if you think about this equation, it can be seen that if you want a larger amplitude of oscillation, then you could do a few things. First of all, of course, you could increase how hard you push it. So you could increase the magnitude of the force, F naught. You could also decrease the damping in the system. Okay, you could try to get rid of the drag, lower it anyway. And another thing that you could do that's maybe a little bit easier than those two things is you can vary the drive frequency. So if you vary and change your drive frequency, and you can see in this equation that as your drive frequency approaches the natural frequency omega naught, then the denominator there will get smaller and smaller, and you'll get a larger and larger amplitude response. So this condition is known as resonance, okay, and we're going to talk about this more and more as we go on. Okay, so one example problem that I want to do is to plot the amplitude versus the drive frequency for an oscillator with a spring constant of 150 newtons per meter, a mass of 100 grams, a damping coefficient C of 0.05 kilograms per second, and a driving force of 15 newtons. Okay, so we're going to need a few constants to continue on using our equation A. So first of all, we need to calculate the natural frequency. Remember that the natural frequency omega naught is equal to the square root of K over M. So if we plug that in, we have the square root of 150 divided by 0.1 kilograms, which is 100 grams, and we find a natural frequency of 38.7 radians per second. Okay. Now another thing we're going to need is gamma. Okay, gamma is the ratio of our damping coefficient C over M. So that's 0.05 kilograms per second divided by 0.1 kilograms, and that gives us gamma is equal to 0.5 inverse seconds. Okay? All right, now what I did was I decided to go ahead and plot this in Excel. And I chose step sizes of 1/3 of a radians per second for my drive frequency, and then I chose a variety of drive frequencies and plotted them. So here's the amplitude response, okay? Now you can see that it's a nice narrow peak, and the peak is located at the natural frequency, which is where we have the highest amplitude response, which is 38.7 radians per second. So that's where we have the largest amplitude. And you can see that it's a very sharp peak and decays off as you get further away from your natural frequency. Okay? All right. Note here, and this is an important idea, the amplitude that I've plotted here is in meters on this vertical axis, and the drive frequency, of course, is radians per second on the horizontal axis. But let's think about that for a second. Look, I can get an amplitude of over 30 meters with this. Now let's think about that. That's actually huge for this system, because if you think about it, Hooke's law says that the magnitude of the force F is equal to kx, the magnitude, right? So that's the spring constant times the displacement. So if I applied a static force of 15 newtons to this oscillator, which was my amplitude, my drive amplitude, if I applied a static force of 15 newtons with a spring constant of 150 newtons per meter, which is the spring constant of this system, by Hooke's law, I would expect to get a displacement of 0.1 meters, or 10 centimeters for a static force. Okay, so when I take that amplitude of force, 15 newtons, and push on it sinusoidally, you can see that the system begins to oscillate with an enormous amplitude that's much, much higher than what we would get for a static force of that same size. Okay, so you can see that you're really putting a lot of energy into that system when you continually pushing on it in that way. All right, so your amplitude is a lot higher for this kind of energy input than it would be from a static pole. Okay, so this is resonance. This is what resonance does. It makes the amplitude response of the system go nuts compared to what it would be if you just gave it a gentle one-time pull. All right. So you can see if I zoom in and I just look at the left-hand side of that plot that I showed you just on the previous slide. I'm plotting here amplitude response versus drive frequency, but now I'm looking at it off resonance. Okay, so I'm just plotting a drive frequency going from 0 to 35 radians per second, and I'm not getting up to the natural frequency of the system, 38.7, so I'm staying away from that. So if you look at that, then if you look far off resonance, right, then the amplitude of oscillation is 0.1 meters. Now that's what we expected from a static pole. Okay, that's what we expected from the static pole. So if you drive the system, but you drive it very far off resonance, then your amplitude won't be larger than it would have been if you just tugged on it one time. Okay, and it's only as you approach resonance that you start to see a larger amplitude response for that system. Now, this can either be a really good thing, if that's what you want, right? Or a really bad thing, if that's what you don't want. It's easier for me to think of examples that are bad things than good things. I can think of a few. Like, for example, bad things. I don't know if you've ever watched the Tacoma Narrows Bridge accident, but that's a very bad thing. You don't want your bridges to have a resonant frequency, a natural resonant frequency that matches the drive frequency of winds and things in the area. You don't want that. Your bridge will collapse. You wouldn't want the natural resonant frequency of the shocks in your car to match the oscillation that you would typically encounter on a road either, because then you'd find yourself just bouncing up and down in your car. That would be bad. Now, when might you want this? Well, if you're trying to have an oscillator and you want it to keep oscillating with very little dissipation, like, say, a quartz crystal in a watch for keeping time or something like that, then you'd want something that is oscillating or being driven near resonance so that it wouldn't lose a lot of energy over time. Okay? So those are some examples and counterexamples of when resonance is a good thing versus a not a good thing. Okay? But it's always something that you need to think about and consider. Okay, so that's the amplitude response of a system. Now, of course, we know that the energy of a mechanical oscillator is proportional to the amplitude squared. Specifically, the max energy in the oscillator at a given time is 1/2 Ka squared. So we can examine this energy as a function of the drive frequency. All right, so what I've done here is I've plugged in the equation E is equal to 1/2 Ka squared, where A was the amplitude response that I've been showing you on previous slides. So I just squared that amplitude and stuck it in this equation. Okay, so if you do that, then you get the energy is equal to 1/2 k times f naught over m squared divided by omega naught squared minus omega d squared plus gamma squared times omega d squared. All right, now if you'll notice, you have a k over m there because you have that f naught over m squared and you have the k out front. So you can borrow one of those m's in the denominator of the f naught over m and pull it out front, and then k over m is omega naught squared. So that gives you the energy is 1/2 f naught squared times omega naught squared divided by m times 1 over omega naught squared minus omega d squared squared plus gamma squared omega d squared. Okay. All right, so that's the energy. Now let's think about what's happening as we near resonance. As we near resonance, the derive frequency is approximately the same, or it gets really close to omega naught. So if you think about what's happening in the denominator of our little fraction over here, we've got an omega naught squared minus omega d squared. Now you can expand that, simplify that, and write it as omega naught minus omega d times omega naught plus omega d. Now, here's where the approximation comes in. If the derive is close to the angular frequency, then that omega naught plus omega d is approximately 2 times omega naught. So I can write that out front. And then I have omega naught squared minus omega d squared is 2 omega naught times omega naught minus omega d. Now, carrying that through so that we're still looking at the energy near resonance, I can say that the energy near resonance is approximately equal to 1/2 f naught squared omega naught squared over m, that's the stuff out front, that hasn't changed, but now I can plug in 2 omega naught times omega naught minus omega d into this square here. So if I do that, that becomes 4 omega naught squared times omega naught minus omega d squared, right? And then plus gamma squared, and now if omega naught is approximately the same as omega d, I can just sub in for that. So it's gamma squared times omega naught squared. All right, that means that from this denominator in this fraction here, I can factor out 4 omega naught squared from both terms. If I do that, then out front I'll get a 1/8, right? 1/8 f naught over m. And now, if I factor out that omega naught squared, it cancels out with the omega naught squared in the numerator. And so I can strike those out, right? So that's gone. And then my fraction is just 1 over omega naught minus omega d squared. And then because I pulled out a factor of 4, the second term is gamma over 2 quantity squared. Okay? So this is the energy near resonance, okay, where omega naught is approximately equal to omega d. So let's plot this function. Okay, let's plot this function. So this goes back to our little resonator in our example problem that had the spring constant of 150 newtons per meter and so on and so forth. Okay? So remember that for our example, we had gamma was 0.5 inverse seconds and our natural frequency was 38.7 radians per second from our little example. So doing that, I just plotted in Excel that function, right, that I showed on the previous slide. This one right here, 1/8 f naught squared over m, 1 over omega naught minus omega d squared plus gamma over 2 squared. I plotted that for energy versus derive frequency. Okay? Now, the curve that you see here has a very characteristic shape that we talk about a lot in physics, and it's called a Lorentzian function. Okay, so this is a Lorentzian curve. This curve is typical for energy spectra. So if you are a spectroscopist, if you're an astronomer and you look at spectra there, anything like that, you might run into this shape. Okay, so since this is a pretty typical shape, people have some nomenclature, some jargon that they use when they talk about these curves. See, not just where the curve is located, so you can say where the peak is, so that's right, where the maximum amplitude response is, that's the location of the peak, and that would be omega naught, right? That's where the resonant frequency is. But you could also talk about how wide that curve is, okay? So you can talk about a bunch of things, the location of the peak, the amplitude of the peak, and the width of the peak. And these are all things that are used to talk about spectra, okay? So when you're talking about the width of the peak, you can see that the width actually varies, right, depending upon, you know, where you want to define the width as. So what people decided to do was, a typical choice is the full width half max. So what they do is they look at what the peak is, right? And then they take half that peak height, and they look at the width at half the peak height. And that's how they define the full width half max of the curve. Okay? So that's the nomenclature that they use. Full width half max, which is often used as an acronym, FWHM. Okay? Alright, so I'm now going to prove that for our curve right here, the full width half max of our curve can be related to the quality factor Q of the oscillator that we defined in a previous lecture. Okay, so here we go. First of all, we have to find what the maximum of the energy resonance curve is. Then we can take half of that, and then we can find what the width is at half max. So that's the procedure. So here we go. What is the maximum of my resonance curve? Well, my maximum energy would be when the drive frequency equals the natural frequency omega naught. So if I plug in omega drive equals omega naught into my equation for my energy, then I end up with a maximum energy, right? That's where my maximum energy response is, of 1/2 F naught squared over m gamma squared. And that's because this omega naught minus omega d thing, that goes to 0. Okay? So that's my max. Now, I'd need half of that because I want to know what omega drive is when I'm at half of this maximum energy. So that means that at half max it would be 1/4 F naught squared over m gamma squared. And now I'm going to set that equal to my energy equation, and I'm going to solve for what omega drive is when it's at that value of the energy. So I have 1/4 F naught squared over m gamma squared is equal to 1/8 F naught squared over n times 1 over omega naught minus omega drive squared plus gamma over 2 squared. Okay, so now it's just some algebra, right? I got some things canceling out. The F naught squared, the m cancels out, right? And then the 1/4 cancels partially out with the 1/8, leaving me with the 1/2 on the right-hand side. So I have 1 over gamma squared equals 1/2 times 1 over omega naught minus omega drive squared plus gamma over 2 squared. So now I just have the denominators being interesting, right? And the numerators are all just 1. So I take the inverse to make my algebra a little bit easier, and I end up with gamma squared is equal to 2 times omega naught minus omega drive squared plus gamma over 2 squared. So I divide both sides by 2, and then I subtract gamma squared over 4 from both sides, and that leaves on the left-hand side gamma squared over 4 equals to omega naught minus omega drive quantity squared on the right-hand side. So if I take the square root of that, then I end up with omega naught minus omega drive, and that's equal to plus or minus gamma over 2. Okay, now this omega naught minus omega drive, that's half the width of my curve, because the center of my curve is at omega naught, and omega drive would be to the left of that on the curve and to the right of that on the curve. So, twice omega naught minus omega drive would be the full width half max of my curve. So that means that the full width half max of my curve, which is often called delta omega, is equal to gamma. Okay? Remember that gamma is c over m. So delta omega is equal to gamma is the full width half max of my curve. Now, earlier we defined our quality factor, right? We said that our quality factor was equal to the frequency divided by the damping. So if you're near resonance, then that's omega goes to omega naught, and then the damping gamma goes to delta omega. So you can say that your quality factor is equal to where the peak is located at resonance, the resonant frequency omega naught, the natural frequency, divided by the full width half max of your curve, delta omega. Okay, so that's how your quality factor is related to the full width half max. So what people generally do if they want to know what the quality factor of a resonator is that they hook that resonator up to some kind of circuit which drives it at different resonant frequencies. Okay, they ramp through the resonant frequencies and plot the amplitude response as they vary the drive frequency, right? They plot the amplitude response as they vary the drive. They see where the peak is located, that's the resonant frequency of the oscillator, and then they fit that peak to a Lorentzian and figure out what the full width half max of that is, and then they take their peak location, the resonant frequency, divided by the full width half max, and that's their quality factor. Okay? So that's what they do. So let's finish up our example, okay? In our little example problem, what would the quality factor have been? Okay? Well, our quality factor would have been the resonant frequency, omega naught, divided by gamma. So that's 38.7 radians per second divided by 0.5 inverse seconds, and that gives us a quality factor of about 77. Okay. Now the maximum energy at resonance would be 1/2 F naught squared over m gamma squared. So for our little example, F naught was 15 newtons, right? That's the drive amplitude. The mass was 0.1 kilograms, and gamma again was 0.5 inverse seconds. So plugging into that equation, I end up with an energy of 4,500 joules. So just to remind you, this was the plot that we had of the energy versus the drive frequency for the oscillator. And you can see that my peak doesn't quite get up to 4,500. It gets close, but it doesn't quite get to 4,500. And that's likely because what happened was, of course, I told my drive frequency to increment in 1/3 radian per second per step. So as I incremented, I probably missed it. No big deal, right? All right, well, I hope you understood all that, and I'll see you in class.